to introduce complex numbers, let's start from solving a quadratic equation, x squared plus 2x plus 2 equals 0. We know from the formula, the solutions are -2 plus minus root 2 squared minus 4 times 2 over 2. The discriminant is -4, which can be written as 4 times -1. Root 4 is 2. So root -4 can be written as 2 times root -1. Therefore, the two roots are -1 plus minus root -1. Previously we say this equation has no real solutions. Now we introduce a new number I. It is an imaginary number, and equal to root -1. I squared is -1. So the roots are -1 plus minus I. A complex number z is a plus bi, where a and b are real numbers. A is the real part, and is written as REZ. B is the imaginary part, and is written as IMZ. When b is 0, z is a real number. When a is 0, z is an imaginary number. If two complex numbers a plus bi and c plus di are equal, then their real parts and imaginary parts are equal. That is, a equals c and b equals d. And vice versa. Z's conjugate is a minus bi, and written as z star. Z and z star are conjugate pairs. Z times z star is a plus bi times a minus bi. This is a squared minus bi squared. Bi squared is b squared I squared. I squared is -1. So the product of z and z star is a squared plus b squared. You can add, subtract, multiply and divide complex numbers. To add or subtract two complex numbers, you add or subtract the corresponding parts. A plus bi plus c plus di is a plus c plus b plus di. For example, 3 plus 4i plus 5 minus 6i is 8 minus 2i. A plus bi minus c plus di is a minus c plus b minus di. For example, 3 plus 4i minus 5 minus 6i is 3 plus 4i minus 5 plus 6i, which is minus 2 plus 10i. You can multiply two complex numbers like you multiply two polynomials. A plus bi times c plus di is ac plus adi plus bci plus bdi squared. I squared is -1. So the result is ac minus bd plus ad plus bci. For example, 3 plus 4i times 5 minus 6i is 3 times 5, which is 15, minus 3 times 6i, which is minus 18i, plus 4i times 5, which is plus 20i, minus 4i times 6i, which is minus 24i squared, or plus 24. So the result is 39 plus 2i. When you divide two complex numbers, you multiply the conjugate of the denominator on both sides. We know from the previous slide, the product of a complex number and its conjugate is a squared plus b squared, and it is a real number. For example, let's calculate 3 plus 4i over 5 minus 6i. Let's multiply 5 plus 6i on both sides. The denominator becomes 5 squared plus 6 squared, which is 61. The numerator becomes 15 plus 18i plus 20i minus 24, which is minus 9 plus 38i. So the quotient is minus 9 over 61 plus 38 over 61i. For quadratic equations with complex coefficients, we can use the formula to find its roots. For example, x squared plus ix plus 2 equals 0. The discriminant is I squared minus 4 times 2, which is minus 9. So using the formula, x is minus I plus minus root minus 9 over 2. Minus 9 is 9i squared. So root minus 9 is 3i. Therefore, x is either I or minus 2i. Non-real roots of polynomial equations with real coefficients occur in conjugate pairs. Be careful that this is only true if all coefficients are real. For example, the above quadratic equation has a complex coefficient I, so the roots are not in conjugate pairs. Let's look at an example. Given minus 1 minus I is a root of equation 2x cubed plus x squared plus 3x minus 2 equals 0, find the other two roots. Look at the cubic equation, we can see that all coefficients are real. So another root must be minus 1 plus I. We already know two roots. So the quadratic factor is x minus minus 1 minus I times x minus minus 1 plus I. Open it up and it becomes x squared minus minus 1 minus I minus 1 plus ix plus minus 1 minus I times minus 1 plus I. This is x squared plus 2x plus 2. Divide the two polynomials, we get 2x cubed plus x squared plus 3x minus 2 is x squared plus 2x plus 2 times 2x minus 1. This is 0. So the third root is half. You also need to be able to find the two square roots of a complex number. For example, find the two square roots of 8 minus 6i. Let the square root be a plus bi, where a and b are real numbers. Then a plus bi squared is 8 minus 6i. Open the brackets, a plus bi squared is a squared minus b squared plus 2abi. So we get two simultaneous equations. A squared minus b squared equals 8, and 2ab equals minus 6. From equation 1, we get b squared is a squared minus 8. From equation 2, we get ab is minus 3. So a squared b squared is 9. Put b squared equals a squared minus 8 into a squared b squared equals 9, we get a squared times a squared minus 8 is 9. This is 8 to 4 minus 8a squared minus 9 equals 0. Factorize it, we get a squared plus 1 times a squared minus 9 equals 0. Since a is real, a squared cannot be minus 1. So a squared is 9. Therefore, a is plus minus 3. Since ab is minus 3, we get, when a is 3, b is minus 1, and when a is minus 3, b is 1. Therefore, the two square roots are 3 minus I and minus 3 plus I. In this class, we learned I equals root minus 1, I squared is minus 1. A complex number is z equals a plus bi, where a and b are real numbers. The real part REZ is a. The imaginary part IMZ is b. A plus bi equals c plus di, is equivalent to, a equals c and b equals d. The conjugate z star is a minus bi, and z times z star is a squared plus b squared. When you add or subtract two complex numbers, you add or subtract the corresponding parts. You multiply two complex numbers like multiplying two polynomials. When dividing two complex numbers, multiply the conjugate of the denominator on both sides. Non-real roots of polynomial equations with real coefficients occur in conjugate pairs.